Good afternoon, students. I realized that my last video was over 41 minutes. Apologize, I didn't mean to go so long. I just had a lot to share. I probably should have broken into two videos. Either way, you would have had to watch them both, so um, you'll have to deal with the long video this time. Anyway, so we're in lesson 6.2 right now. It's on page 390 if you have your textbook with you. It's solving systems by substitution. Now, in the first lesson, I taught you how to solve a system, just so you can see all the words. I taught you how to solve a system by, what's it called? Oh yeah, by graphing. So basically the idea was you have two equations, graph both lines, make sure that you have enough points that you graph them to the point that they cross. Now if they cross at an exact point, like 2, 4 or something like that, it makes it easy. They may cross like somewhere where it's not exactly on the graph paper, like right on a corner. So for example, it could graph at like 1.5, 8, something like that, or 1.5, 8 and 3/4. So in a case like that, I've always wanted to do an example of this. So let's just say you have a line here. Now, normally when you think of a point, you always think of a point as you can see right on the corner of the graph paper. Now, if there's one fraction in it, then your line is going to graph not on a corner, but it's going to graph on one of the lines of the graph paper. See how I'm graphing on both lines of the graph paper there, but here I'm only graphing on one line. Now, if both of your items have fractions, then it's going to graph off of the grid. So you can see here, I have no corner, I have no line, I'm just graphing in like the center of the square, the little square. I'm talking about the little squares on the graph paper. I'm hoping that that's clear. But yeah, so just so you know, when you graph, if both points are whole numbers, it will graph to a corner of your graph paper. If one of them is a whole number and one has a fraction or decimal, then you will graph on a line but not on a corner. And if both of them are fractions or both of them are decimals, then you will graph in the middle of a square somewhere but not touching. Now with those middle ones, sometimes you have to estimate, okay? Like for example, if one of your values was 1.8, then you would want to graph it like probably higher, assuming that this line represents 9. If it was 1.5, you would want to graph it in the middle. If it's 1.2, you would want to graph it towards the bottom. So see, you have to kind of guesstimate there. All right, enough about that. That was just a little side lesson, something I've been wanting to say for a while about graphing with when your numbers end up being non-whole numbers. Let me move myself back up here since we already read. All right, so this lesson will answer two questions. Question 1 is how do you solve with two variables? And question 2 is how do you solve without making a graph? Okay, so now we've had some lessons where there are two variables in it, and one of the things that you've done, especially once we started with doing linear equations, is we don't exactly solve for both variables. We just sort of like organize it so it's easy to put in values. Now the x values oftentimes are either given or you're told, okay, we'll just make up an x value, okay? Especially like when you have y equals mx plus b, it's very easy to make it an independent value, 0, 1, or 2, or something like that, so that you can use the equation to find your independent value so you can know what y is, okay? But sometimes none of that information is given, or maybe if you're not graphing and you all of a sudden you have two variables in an equation, you're like, how are you going to solve them? So I have an example here to show you. So let's just say you have a word question about buying tickets to go to a show. And adult tickets cost $10 and kid tickets cost $5. Okay? So let's just say that you have 2 adults and 3 kids attending the show. So now I have 2 variables, 2a, a meaning adults, plus 3k, k meaning kids. Now, let's just say for whatever reason I didn't know one or both of these values here. Obviously I know the values, so it should be pretty easy to solve. 2 times 10 for adults plus 3 times 5 for kids, okay? But let's just say for whatever reason we did not know that information, okay? And you just have an equation that has 2 variables in it. Well, how on earth do I know what a and k are unless that information is given like it is here? Well, there's a hint I want for you to know, and that is that you can rename one variable in terms of the other. Okay? Let me give you an example. Adult tickets can be known as 2 times the kid tickets because they're twice as much. Or kid tickets can be known as 1/2 of the price of the adult tickets. So suppose I want to make one variable in my equation here. I know that a can also be called 2 times k or just 2k. So in that case, what I can do is instead of a in my equation, I can substitute 2k. So now I have 2 times 2k plus 3k is equal to, whatever my answer would be. So I would multiply 2 times 2k is 4k plus 3k equals what? So in that case, 4k plus 3k would equal 7k. And I can look over here and see k is $5, so that would be $35. Okay? I said okay after using the letter K so many times. Now, I wanted to show you how you can do that simply by substituting. Instead of calling this A, I called it in terms of the other variable. Or in other words, instead of calling it A, I called it 2 times K. It's kind of like, some people may joke like this, especially if they like math. And you ask, oh, well, how much is a kid ticket? Oh, well, it is 10 divided by 2. And it's like, well, why didn't you just say 5? Oh, well, I just wanted to be silly and very literal. Sometimes people will do things like that. I've jokingly said how much, someone asked how much is something, the price was $1, and I'm like, oh, it's 100 pennies. Just as a joke, because you hear 100, you think it's something large, and it's like, oh, but it's pennies, so it's small. So all you're doing is just renaming one value in terms of the other, okay? 100 pennies is $1, and one adult ticket is 2 times a kid ticket, okay? Now, let's go ahead and solve this a different way. So the kid ticket is 1/2 of the adult ticket. So instead of K, I can call it 1/2 A. So now, in this case, I'm still solving the same equation. I'm just solving it a different way. Okay? So I have 2a plus 3 times 1/2 a. So 3 times 1/2 would be 1.5 a. So I have 2a plus 1.5 a. Okay? So that would be 3.5 a. So let's see, adult tickets are $10, so 3.5 adult tickets equals $35. Okay, so I'm still solving it. May have been a little more complicated with this way because I had fractions involved. But the point is, I have now changed both equations to one variable instead of 2. See, now I have like terms A and A here. I have like terms K and K here, okay? As opposed to having 2 different non-like terms, A and K. So another hint, if you may solve each variable first, the order doesn't matter. So you may have noticed I solved for the variable a in this equation, and I solved for the variable k in this equation. Doesn't matter, I could have done k's here and a's there. The idea, or why I said that, is because when you're solving by substitution, or substituting the value of one equation into a variable for the other, you're going to end up sometimes having to decide, well, which one should I do first? So the truth is, it doesn't matter which one you do first. You'll still get the right answer, provided that you do all the steps correctly. My recommendation would be the one that you do first is the one that's going to be the easiest or the least amount of steps. So the second question is, how do you solve without making a graph? You may remember in the last lesson, it was like, oh, this is nice. All I have to do is make a picture. And after you make like 20 pictures and 20 graphs and use up all your graph paper, you're tired of making pictures. It would just be kind of nice to like have a mathematic way of solving this. Easy. The steps are to substitute one equation for a variable in the other equation. So I'm going to quickly read through the steps, but then I'm going to go over them as we're going to actually solve some equations here. Okay, let me get my arm out of the way. So here are the 5 steps to solving by substitution. Number 1, pick the equation with the isolated variable or the easiest to isolate. Step 2, substitute the value of the isolated variable in terms of the other variable. Number 3, solve for the other variable. Number 4, use the solution in either equation to solve for the first variable. Number 5 is to state the solution as an ordered pair. Now I know that reading those, you might have been like, you're going too fast, or that doesn't mean anything to me. So let's look at the steps when we actually go ahead and solve. This is problem 1. It is actually in your textbook. I believe it's on page 390 or 391. So let me go ahead and do this problem. So I have 2 equations, and I am told that these equations make a system, which, as you remember from the last lesson, if I graph it, it means I'm going to have a blue line and a red line that cross at some point on the coordinate plane. But I'm trying to save time and paper and not graph it. So my first equation, y equals 3x, is blue, and my second equation, x plus y equals negative 32, is red. The colors don't matter. The purpose of the colors is just so that it's easy to separate between the 2 equations. Now, when I look at the first equation, I look at my first rule here. It says pick the equation with the isolated variable. Now, I have x and y in both equations. In this equation, x and y are together, but in this equation, y is by itself. X is stuck to 3 because 3 is being multiplied to it. So the one that I'm going to logically choose is the one that is completely isolated, and that is y. And remember, isolated means that it is by itself on one side of the equal sign. Okay? So in that case, if y is equal to 3x, then I can actually call it 3x. So I would say it like this: y is equal to, and I'm color coding it here for a purpose, 3x. Why do I say that? Well, because in my next equation, I'm going to do this. X plus, I'm going to leave a nice big spot here where y is supposed to be. And I'm going to substitute in the value of y. Okay, since y equals 3x, then I just, instead of saying x plus y equals negative 32, I say x plus 3x equals negative 32. How do I know? The first equation tells me one of the values in the second equation. How can it tell me that whole value? Well, easy. Y is completely isolated, so then I know that the value of y in either equation is 3x. So therefore, by renaming it 3x, I have now eliminated one variable. I have x plus 3x is equal to negative 32. So now I can go ahead and solve. X plus 3x is equal to 4x. Isolate, opposite both. I simplified by combining like terms here. Now I'm going to solve. Negative 32 divided by positive 4 would be negative 8. Aaliyah, that's right. I know that that's what you said right now when you were watching the video. So x is equal to negative 8. Now, it's tempting to think, oh, that was not that hard, and I'm done. But we're not done just yet, okay? So let's look at the steps we did. We picked the equation with the isolated variable. We substituted the value of the isolated variable in terms of the other. Since y was isolated, we called it 3x and then substituted it instead of y in the second equation. And then I solved for the other variable. So I solved for x in this case. In this case, x would be the other variable. Well, let's look at step 4. Use the solution in either equation to solve for the first variable. So what that means is, since I now know what x is, I can now solve for y. But Mr. Bauer, you know what y is. Y is 3x. I know, but I have two variables here, so it is not in solution form. So here's what I'm going to do. See where it says y equals 3x? I am going to substitute the value of x for x. See why I color-coded that? The value of x, I'm now substituting it again. So I have to do this twice, is what I'm trying to tell you. So 3 times negative 8 is negative 24. So y equals negative 24. Now I have two solutions. Okay, well, Mr. Bauer, that was great. We did step 4, so are we done now? One more thing, and this one's actually pretty easy. State the solution as an ordered pair. Now, as you remember, every ordered pair is an x value first and then a y value. And as you probably already remember from lesson 6.1, that the solution to a system of equations is an ordered pair. So my x value is negative 8, and my y value is negative 24. So the solution to the system is negative 8, negative 24. Okay? Now, let me follow the steps. Number 1, pick the equation with the isolated variable. Number 2, substitute the value of the isolated variable into the other equation. Number 3, solve for the other variable. Remember that this one had y isolated, but we're solving here for x. I got the value of x. Step 4, use the solution in either equation. So I could put negative 8 here and solve for y, or I could put it here and solve for y. It would work in either equation. Okay, and I can show you, I don't want to do the whole thing, but if I had negative 8 plus y equals negative 32, I would add negative 8 to both sides. Negative 8 from negative 32 would raise it up to negative 24, which is its value. Okay? Now, then after I solve that, I substitute it into the first equation, or to either equation, and then I get the value of the y. And then I state it as an ordered pair. So what I don't want to happen here, I'm going to cover up my answer here. What I don't want to happen is, okay, I get to here and here, and I'm done. Just make sure you do that one last statement. I'll probably give you full credit because if you got both solutions correct, but it just makes it easier if you actually write the answer in the form that I'm looking for. Okay, got that? Let's go ahead to problem 2, and in your book it's on the next page, I believe. Here's another system. It's 3y plus 4x equals 16, and negative 2x plus y is equal to 2. All right, so the first step, pick the equation with the isolated variable. Well, both of my variables are on the same side. Both my variables are on the same side. Ouch. So what do I do? If you look here, there's these words, or easiest to isolate. Let me just point that out there. You want to pick the one that has the easiest to isolate. Now, is it necessary to pick the easiest one? Feel free. Go ahead and pick the hardest one. Nico, if you want to go ahead and pick the hardest one to isolate, or Evelyn, go ahead. But it's just going to take you more time. So my recommendation would be to pick the easiest one to isolate to take less time. Now, if I look at all my variables, 3y is being multiplied and has 4x added to it. 4x is also being multiplied. I don't know, unmultiplying is a little bit harder than unadding. It's like easier to subtract something than it is to divide it. So let's go to this one. I have negative 2x, obviously has negative 2 being multiplied to it, and y has, well, nothing. It has 1 being multiplied to it, so 1 times y is still y. So the variable that I'm going to choose to isolate is y, because it's the easiest to isolate. Why? Because it's the easiest to isolate. That was a pun. Sorry, I'm a dad, so I can say dad jokes, and 2 days ago was Father's Day. Moving on, so let's go ahead and isolate this one. Remember, isolate, opposite, both. So I have y, I have 2x, negative 2x being added to it, or I can think of it as 2x being subtracted from it. Either way, the opposite of negative 2x is positive 2x. So now I'm going to add 2x to both sides. Now that I've done that, in simplest form, I can write that as y is equal to 2x plus 2. Now you notice that I switched the order so that it is in slope-intercept form. Okay? Just make a habit. It's just preferable to have it in the form that's easiest for you to solve. Okay, so now y is equal to 2x plus 2. So I'm going to go to the other equation, and I'm going to rewrite it as 3. Where there is a y, I'm going to leave a nice big parentheses because I'm substituting, plus 4x equals 16. Okay, now the value of y, since y is isolated, is 2x plus 2. So I'm going to substitute that whole thing in here, 2x plus 2. But wait, I took an entire expression, like almost a whole equation, and stuffed it into the other one. Yeah, that's right. Any problem with that? Point being, when you substitute, you're going to be putting a lot of stuff in sometimes. So it's a good thing you probably remember distributive property from about 3 weeks ago. But in case you don't, I'll go through the steps. 3 times 2x is 6x. 3 times 2 is 6. So I have 6x plus 6 plus, and I'll just change colors at this point, 4x equals 16. Now I want to combine my like terms. I have 6x and 4x would be, yep, Isai, that's right, 10x. And who remembers what's next? Yes, Evelyn, you're right. I subtract 6 from both sides. And I end up with 10x equals 10. Then I divide both sides by 10. I think I'm almost to the bottom here. Let me just move this up. Okay, divide both sides by 10. And I end up with x equals 1 as my solution. Now you may want to remember, I'm not done at this point, okay? I have to substitute 1 into either equation, okay? So I can put it into the blue equation or the red one. I'm going to choose the red one because the red one looks like I have less steps. So I have y is equal to 2. Instead of x, I'm going to substitute in 1. Okay, so 2 times 1 is 2. 2 plus 2 is 4. So y equals 4. Now I have both my solutions, but I want to state my answer as an ordered pair. The solution is the ordered pair 1, 4. Or if you were to graph it, that is the point on the graph paper where both lines meet. But remember, the point of this lesson is to show you how to do it without the graphing. All right, hope you enjoy, and thank you very much.